Welcome to another optimization video. So we have an open rectangular box with a square base, and we've got 48 square feet of material, and the dimensions we're looking for are the ones that are going to make the largest possible volume. So I've already drawn the picture. I've labeled things. Again, I would recommend a good choice in this case would be H, L, and W for length, width, and height. And remember, open, it says open box. In this case, that means that we've got no lid. And so we're given that the surface area, that's the cardboard or whatever it's made out of, that material is 48 square feet. And our goal is to maximize the volume, which the volume of a rectangular box is just length times width times height. And so currently, I just want to point out, this currently is a function of like 3 different variables. And so that's a big no-no at the moment. We're going to try and get that down in terms of just one variable, right? Our goal is to get everything just in terms of one variable so we can think about it as a function, we can use calculus, we can draw a graph. And so we have to think about how we can take the given information, right? We have a given information about surface area, and we could try and write down an equation for that. And you might think, oh, that might let us solve for one variable in terms of the other. But what are we going to do with the other? We've got 3 variables right now, right? How are we ever going to get from 3 variables all the way down to 1? And there's one key word in the original statement that I wonder if you notice. So pause the video and see if when you reread the statement, if there's any other simplification that we can add in. All right, so I'm going to reveal the answer in 3, 2, 1. It's this square base. So if we have a square base, well, we're also given that there's a square base. So that must mean that the length and the width are actually going to be equal, right? And the way we've drawn it, our base is going to be represented by L and W. And so in this case, those are actually going to be equal. And so let's just turn everything in terms of L. So in fact, let's just call that L. We can kind of leave that in there. And now when we're thinking about our volume, well, now we know what width is, right? Width is the same as L. So it's just going to be L squared times H. That's pretty good. And now we're down to something with only 2 variables. Okay. Still no good, right? We still have to kind of get it down in terms of one variable if we're going to think about graphing anything or using calculus. And so now what we're going to have to do is now we're going to have to work out what that surface area is, right? And so let's take that surface area and study it. So how many sides does our box have? Well, normally a box would have 6 sides, top, bottom, and the 4 sides. But this one doesn't have a lid. And so if we think about what that surface area is, it's going to have 5 different parts, right? It's going to have the bottom. And maybe I'll try to shade these in as I go. So the bottom is going to have area L squared. The left and right sides, let me try and shade those in this way. So the left and right sides are going to be L by H. So these orange side here, and this orange side here, that's going to be H. That's how tall it is going to be H by L. So I have H by L, that's the left side and the right side, and there are 2 of them. So I need to add 2 times that. And then finally, the other sides, maybe you'll do that in green. So this side here, the front and the back, those are going to be the same size. Well, if we think about it, those are all also going to be L by H. So these front and back sides, because of the square base, those are going to have the same side there. And so we have our bottom and our sides. And if I simplify all of this, what equation am I going to get? Well, I'm going to get L squared, do it black, L squared plus 4HL equals 48. I'll leave the units out because we're just going to focus on the equation. And I look at that equation and I think, is this an equation I could solve for one variable in terms of the other? Could I solve that for L? Could I solve it for H? Now the answer to both of those questions is yes. But solving for L, because we've got an L squared, would actually require the quadratic formula. And I'm not interested in doing that now because that would make it messy. And I noticed that if I want to just solve for H, that would be a lot simpler, right? Solving for H isn't so bad. And so let's take that equation and solve it for H. Again, now would be a great time to pause the video and see if you can solve for H yourself, because I'm going to do it in 3, 2, 1. I'm going to get 4HL equals 48 minus L squared and get the term with H by itself. And then I'm going to divide both sides by 4L. So all that's left here is H. And now I'm going to get 48 over minus L squared over 4L. So this is my formula for what the height will be in terms of the length, given that the surface area of this cube, or this, sorry, it's not a cube, but of this box is going to have 48 square feet of surface area. So really good, really good. Let's take that and let's see if that helps us with our goal. So our goal was to maximize volume. And at the moment we had the volume, we had simplified it down to length times width. So that was, those are the same. So that was length squared. And then we need to multiply by the height. And now we can actually use this expression here to get all of this into one variable. So this is V equals L squared times 48 minus L squared over 4 times L. And so now we have a function of one variable. This is now a function of one variable, which is great news because we know how to find the maximum of any function of one variable by looking at endpoints, by looking at critical values and things like that. And so I first want to do, before I do anything else, I just want to say, okay, we've got a function of one variable L. I am going to simplify this a little bit. I can cancel the factor of L with one of the factors of L in the numerator. So at the beginning, I'm going to pull the 4 in the denominator out front. So I'm going to get 1/4 of L times 48 minus L squared. And I'm going to simplify this one more step by distributing so that my derivative is a lot easier. So I'm going to get 1/4, let's see, 1/4 times 48 is 12. I'm going to get 12L minus 1/4 L cubed. And again, I'm going through the algebra here, but I recommend you pause the video and make sure you can do these steps on your own and try to see kind of how I'm going from one step to the other. Okay? And so awesome, awesome, awesome job. And so now what we have is we have our function for our volume. And so our goal now is to think about how to find what the maximum could be. And so now what we have to do is we have to think about our domain for our length. Now, the length always has to be at least 0, right? We can't have negative lengths. But if you think about it, if we're going to be using 48 square feet of of cardboard or whatever our box is, we need L squared, right? We need L squared material just for the bottom. Okay? And so no matter what, L can't be too big, right? Like L can't be like 8, for instance. What if L were 8 feet? Well, then we need 64 square feet just to do the bottom. And so we actually have a restraint on the domain that L can't be any bigger than the square root of 48. But I want to point out to you that we're going to see this really doesn't matter. Because if you think about it, if you made L as big as you could, right? Really stretch it to the limits. Well, that's going to mean you used all of your cardboard just to make the bottom. And so how much are you going to have left for the height? You're not going to have anything left. And so if that were the case, your volume's going to be zero. And we can see that, for instance, here, if we plug L equals square root of 48 in, this factor is going to be zero. And so in a lot of these problems, what will happen when we test the endpoints, we're going to get volumes of zero. Right, so these represent the case when the length was zero. This is going to represent the case when the height is zero. And of course, if the length is zero or the height is zero, then your volume is going to be zero. So again, we're going to be interested in values in between these two ranges. So let's see if we can do that. So that's going to be the critical values. So now we're looking for critical points. So these are going to be points where v prime of L is equal to 0 or undefined. But of course, our function is a polynomial. Its the derivative will be a quadratic. We can always, that'll always be defined. The only thing that can happen is it might equal 0. And so if we do that, we're going to solve that. So what's our derivative? Our derivative v prime. So if this is our equation for v, then v prime is going to be equal to 12 minus 3/4 L squared. And so if I take that, I set that equal to 0. So now I have that. And now I'm going to get 3/4 L squared equals 12. And if I solve that for L, I'm going to get L squared equals, right, I'm going to multiply both sides by 4. I'm going to divide both sides by 3. And so what I would get is 16. At the end of the day, when I solve that, maybe I'll just go back and clean that up. I'm going to get L squared equals 16. And so that will imply that L is going to equal plus or minus 4. And I hope you're thinking, wait a minute, L can't be negative. You're right. We said our domain was that L had to be positive because it's representing a length. So the only solution that we really care about is going to be L equals 4. And so now let's check what that is. So at L equals 4, we can plug in our volume. So remember our V of L was, what was it, 12L minus 1/4 L cubed. So if I plug in 4, what do I get? Well, I'm going to get 48. That's 12 times L minus 1/4 times 64, which should be 16, which at the end of the day is going to equal 32. And so what this shows me is that, so since we tested the endpoints and all critical points, we know the maximum happens when x equals, oops, sorry, our variable is called L, when L equals 4. And in that case, the volume is equal to 32. So what we should do now is we should finish the problem by giving all the dimensions of our box. And so remember, our box had a square base that was L by L, so that's going to be 4 by 4. And then what was our formula for the width? Let's see if I have it pasted still, or for our height. So our height is actually given by this formula here. So our height is going to be 48 minus L squared over 4L. And so in this case, our height is going to be 48 minus 16 over 16, which I think if I did that correctly, will be equal to 2. And so if I wanted to draw in beautiful box, I'm not doing so well at the moment. I have to fix up some things. But I think that the dimensions of our box would be 2 by 2 by 4, and that would be the dimensions of a box that has the maximum possible volume, um, given that the surface area is equal to 48. So I'm trying to shade it in so that the top is open. I don't know really how to do that without shading everything in. Um, but yeah, thanks for watching, and comment, let me know if you have any questions, and I'll see you soon.